Now we move on to the derivative, okay, the actual rate of change. I can work out what dt on dt is because, it's not one, because I have the function already, right? So let's differentiate. Now, as I do this, by the way, do you remember I mentioned that sometimes you'll leave your equation in terms of the k, because the k is just kind of gross to write, okay? So I'm going to say t is equal to this, where k is, and I'm going to define it. It's kind of redundant to put this in because I've already established this like 3 or 4 lines earlier. But that's only because I did this question right before. So if this question was out on its own, you'd want to say this line. It's kind of important. So that later on when I say k, you know what it's referring to. Okay. Now, differentiate. What happens? The constant will simply vanish, right? And then here, just chain rule, right? So I've got minus 78k e to the minus kt. Now you can see why dt on dt, right? It's not simply your temperature function times the constant of proportionality. It doesn't work, right? Because your temperature function has other stuff flying around. It's got namely this 22. Okay. So there's my derivative in terms of time. So how do I twist and turn it so it is in terms of temperature? Okay, now let me factorize, which doesn't look like it's going to do anything, but hopefully we'll try and make it a little more obvious. To show you, it's actually not that difficult. All I've done is take the minus k out, right? But that leaves me with this 78 business, okay? Now can you see that this is a really important part of our temperature function, right? In fact, it's almost the whole temperature function. All I'm missing is 22, right? So let's put 22 there. Okay, now, pause. That's the temperature function. Okay. In a second, I'm going to substitute that whole thing for capital T, because then it'll be a function of capital T, right? But, as I hope you know, right, we can't just go around willy-nilly adding things on. So if I've added 22, I ought to subtract 22, right? Okay. I can still substitute this part for capital T. So now, I'm basically there. There is my function for how the temperature is changing in terms of what the temperature is. Okay, does that make sense? Now, some of you undoubtedly will recognize this because that is, sorry, that's my red. This line here is it's Newton's law of cooling. Have you done Newton's law of cooling? It looks like this: minus k T minus E, where T is the temperature of your object and E is the temperature of your environment. Okay, 22, temperature of the environment. Okay. We don't use this for the same reason we don't use the physics formulas, because it takes out all of the actual maths that maths is about. Okay, it sort of automates it, right? However, it's still really helpful because can you see we were so close, right? We were really, really close, right? This line up here, despite the fact that I've crossed it out, says how you're changing, your rate of change. It's proportional to your temperature. Okay, but it's not proportional to temperature. It's proportional to the difference in temperature. Can you see that? Okay? Not proportional to the temperature itself, but this difference factor, okay? And what you'll have is this kind of situation coming up all the time when you've got something changing and there's some external constraint on it, right? Like something that's cooling down to an ambient temperature, or for instance, something that's going to reach a natural concentration, or a population that's limited by like food or disease or all those kinds of things. So this difference bit gets at that constraint. Right, we're almost done. Let's just finish off this last bit and just apply it. How long is it going to take to get to 30 degrees? What would you guess, by the way? It took 5 minutes to get to 60 degrees. 5 minutes to get to 60 degrees. 5 minutes to drop 40 degrees off the temperature. So what would you guess? I want you to write down a number. We've got this as our sort of fence post, okay? Just make an estimate. Make an estimate, write it down on your piece of paper so you're committed to it, okay? In pen. And then we're going to do the maths and we'll see how close you were. Okay, so have you all written down an estimate? Got an idea? I can't do it because I'm cheating because I already know the answer. So, let's give it a go. Okay. If I want to get to 30 degrees, all I need to do is take my temperature function, right? Pop 30 on the left-hand side, solve for T. So, let's give it a go. Okay, now, again, I'm trying to emphasize, like, the reason why I don't actually say what K is, even though I know exactly what K is because it just makes this thing take twice as long to write, and it doesn't change any of the numbers that you're working with, right? So I get to this last line, and I'm about to hurl it into the calculator. So, what do you get? Can we get it to 2 decimal places? Anyone got there yet? Anyone? Here's our value K, in case you're wondering. Any takers? Anyone? Anyone? 15.836? 836? 833, so I guess I'll call that 3. Okay, so almost 16 minutes. Who was close? Who was close? What did you get, Jeffrey? 16? Anyone closer?
Oh, if you round to the nearest dozen, I was close.
Oh, okay, yeah, excellent. Yeah, if you round to the nearest 100, I'd be pretty close too. Okay, anyway, alright, well done. Now, 15, okay, about 16 minutes. Does that feel about right? It didn't take long to drop 40 degrees, right? I only want to drop another 30, which is less, right? Why does it take almost twice, more than twice as long to drop that next 30 degrees? Because of what the function looks like. As you're reducing in temperature, you're losing temperature slower and slower. That's why it takes you quite a long time to actually get there. Okay?